Hello, YouTube. Now we started recording the class. So the reading for today it's actually going to be. So when I start, it's sort of like when I write the first slide, I'm not quite sure what's going to happen, and so uh, by the last slide, the first slide is sometimes outdated. So today I think we will actually get through 16.4. Actually, the first four sections of chapter 16 are really just a lot of throat clearing, so to speak. It's just like, well, these are things we'll need later, something we'll need later, something we'll need later. And so we're going to continue that today. And so for Monday, we're going to get to 16.5, and that is where the good stuff starts, where we will actually really get into Galois theory as it is. Anyway, so technically, I think we assigned a due date of today for exam 2, but if it's not done, that's okay. I'm not gonna sweat it, so especially since I haven't graded problem set 7, and I haven't quite caught up on the homework, so I will try to get to that soon enough, and then problem set 8 is due on Monday, April 13th, and oh yes. And I forgot, and of course, all deadlines are last, but I also forgot that there would be a problem session at Friday at 10:30 by Zoom. And so then you all know how that goes, and I think this has actually been working pretty well with this class. So be there or be not on Zoom. I don't know. All right. So are there any procedural questions? Oh, yeah. There's Mengru. Mengru, did you want to say a word on for YouTube? Let me remind you that everybody that we're recording. And so Mengru, did you want to say a word on YouTube as to why you picked that wonderful song? Let's get ridiculous. See, there we go. We've preserved me doing my Red Foo imitation on YouTube for posterity. Mengru, did you want to say how and why you picked that song?
There's no specific reason. I just like the song.
so I did get the right song then.
Okay.
I was just checking. I actually, Mengru and I had a lovely Abbott. I like to think of an Abbott and Costello exchange on email where, well, actually, my wife says it's just you being old, my buddy. So Mengru said, I said, why don't you pick a song? And Mengru says, okay, let's get ridiculous. And I said, yes, we'll be ridiculous, but what song do you want to pick? And so on and so on and so on. Anyway, so yes, old man is old. All right. Shall we just do some math now, or what? I'll take that as a let's do some math right now. Okay, so let's get to it. Sure. Oh yeah. So as always, for the next few, probably for the rest of the semester, I'm going to start every class by putting the same slide, Galois theory in a nutshell. And so so you may notice that this font here is in a different color. Oddly enough, this is supposed to be purple in LaTeX. I'm not sure why it's not a bad color, but I would never call it purple. Anyway, so suppose an extension K of a field F is a splitting field of an irreducible polynomial little f and big F, bracket x. In other words, f of x is a product of linear factors, all of which are elements of the field K. And in fact, K is exactly the field that you get when you take capital F and add on those roots alpha 1 through alpha n. And so, and the reason this is in a different font right now is that that this stuff is what we're doing today. So I will try to. So what I'll do each time is I'll sort of highlight the part that we're introducing as we go along. Anyway, so that's what we're doing today. We're talking about splitting fields, and then anyways, but so given that setup, the point of Galois theory is that it relates the field theory properties of K as an extension of F, and the group theoretic properties of the group of field automorphisms of K fixing F. Oh yeah, I guess we'll also, I should mark that in purple today too. We will, let's see if I can do this. I'm beginning much better about writing with my finger. There we go. Strange skills to pick up during a pandemic. Okay, so another idea that will interest today is the group of field automorphisms of K fixing F. That's called G of K over F. Right. So anyway, so the as and I think actually today we'll do this. We'll get to this part. So what we'll see today is that these automorphisms must permute the roots alpha 1 through alpha n. And anyway, so and then later on we'll show that they're isomorphic to a transitive subgroup of Sn. Anyway, so so the idea is that so again you're looking at the automorphisms of the extension that fix the sort of base field. And as we'll see, actually, I think by the end of today, those automorphisms they're actually they're permutations of the roots of F, and so and later on we'll see that they actually act transitively on those roots, and therefore isomorphic to a transitive subgroup of Sn. So so not only do we just sort of know kind of abstractly the idea of this group of field automorphisms of K that fix F, we're actually sort of able to write down concretely exactly what kind of permutations are in that group. And so the signature, so well, that's all well and good. So there's a lovely general theory, but the real value of the theory comes out in the applications, and sort of the signature problem of the applications of Galois theory is when can those roots alpha 1 through alpha n be written? Question: when can those roots alpha 1 through alpha n be written as a function of the coefficients of f of x, an expression that uses only kth roots? So remember the coefficients. So if again, you always want to think that the base field f is q. I mean, there are other circumstances, there are other interesting cases of this, but usually what you want to think is you want to think, okay, the base field is the rationals. And so the coefficients of f of x will be rational, and usually they'll be integers. And so you might think, well, is there some way of expressing these solutions to f of x equals 0 in terms of roots, in terms of some really complicated version of the quadratic formula? So if that's true, we say that f of x, the equation f of x equals 0 is solvable by radicals. And of course, well, not of course, but if you've seen Galois theory before, the really interesting thing is that we're able to prove that the generic degree 5 polynomial is not solvable by radicals. So anyway, yeah, I guess this last sentence is still correct. Yeah, so we haven't actually really defined anything on this slide, this summary slide yet. But the eventual goal is to sort of fill in all the details of this slide. All right. So any questions so far about kind of the big picture of the 30,000-foot view of Galois theory? All right, so let's move on then. Okay. Right. So this is where this is what we did last time. So just as a recap of last time, we talked about the elementary symmetric functions, and the elementary symmetric functions. Again, it doesn't hurt to repeat the point. The point is that the elementary symmetric functions. Actually, let me get back to the big view. Maybe it's easier to see. The point is that of the elementary symmetric functions, that they relate the roots of a polynomial to its coefficients. Rather, actually, I guess it's express. It's probably better to say to express the coefficients of a polynomial as a function of its roots. So if you ever have thought, well, perhaps it's actually even occurred to you, like maybe thought, like, well, how is it that is there some formula for getting the the coefficients of a polynomial, if you know the roots, well, here it is. I mean, you kind of know what that is for quadratics, and the general case is exactly this: the elementary symmetric functions, and they look kind of like this. And we had a combinatorial explanation last time. This sort of well, the highest degree term has just a coefficient of 1. The next term has a coefficient of negative. The sum of the roots. Then you have the sum of all pairs of products, sum of all triples of triple products of roots, and so on, all the way down to the sum of all n-fold products. And sort of, oh yeah, I guess I should have like some sort of dividing line here. So there's a dividing line between these two things, and then we say that in general, more generally, that we say that a polynomial n variables is symmetric exactly when f is invariant under permutation of the indices. So that's what a symmetric polynomial is. So the symmetric function. Oh, actually, let me. I think we have not. Yeah, well. Let me ask. Let me just pause for a moment here. So, are there any questions about symmetric functions, either the elementary symmetric functions or symmetric polynomials in general?
What does it mean again for it to be invariant?
To be, I'm sorry?
Invariant?
Oh, invariant. Oh, yeah. So, when you permute the, let me do an example. Let's see. I think I should do this with pen. So so what does invariant mean? When n equals 2. Oops. Yeah. When n equals 2. If you have like u1 squared u2, if you have just that, then if I permute 1 and 2, so this by itself is not invariant. I guess. I mean, I somehow I want to say the word variant, but that's not. I'm pretty sure that's not a word. This is not invariant. Because if I switch one, if I permute 1 and 2, if I switch 1 and 2, then I get a different polynomial. So that's what it means to be not invariant, but as opposed to a not invariant. Ha! See what I did there? I got dad jokes. All right. So, but if I sort of add in this other term u1 u2 squared, then this whole, and I look at that entire polynomial, then that is actually invariant. I should make that in green because then that'll match. Because color coordination is what separates us from the lower animals. Nobody seen Steel Magnolias? Great movie. All right. So, oops. Do this. So, Apurva, does that make more sense? That the red and the green together are an invariant polynomial, because if I switch 1 and 2, then I get the same thing, just because it's just the same sum in a different order. Oh, yep. Okay. So yes. All right. So thanks. Thanks. Excellent question. Yeah. Evidently, I didn't explain that. So yeah, that's what I mean by invariant. Right, and actually, this actually illustrates. Well, this is like something that's generally useful. It's something I feel like I've used a lot in my mathematical career. Just this idea. I think we actually did this last time. This idea of symmetrizing. If you sort of take, something that is not invariant under some set of symmetries, and you take, I don't know, like a sum over all possible symmetries, or a product, or a union, or whatever. Then you get something that is invariant. This is symmetrizing, the process of symmetrizing, which if you do group theory kind of stuff, that process really gets you pretty far. So is now everybody good? Should we move on? Okay then. All right. So now moving on. So now we come to, I believe, if I remember correctly, we sort of indicated how the proof of this goes. I'm not sure, I don't think we really into the details, but maybe the details aren't super important anyway. So the symmetric functions theorem says that if G is a symmetric polynomial, then G can be written, as it turns out uniquely, though that's not, we don't really care about that so much, as a polynomial in the elementary symmetric functions S1 through Sn. And so actually, I guess, as an example up here, so yeah, for example, this polynomial up here happens to be equal to S1 times S2. I mean, there's not a whole lot of possibilities for n equals 2, but if you look at it, this polynomial here just happens to be u1 plus u2 times u1 u2, and those are respectively S1 and S2. Yeah, so that's what I mean by polynomial in the elementary symmetric functions. And so the main application of that is suppose little f is a polynomial of coefficients in big F, and little f factors. Well, so basically, when K is a splitting field of, yes, as we shall define in a minute. I guess this is actually the definition of splitting field, more or less. This is, i.e., A is a splitting field of F, or a splitting field of F. And later on, soon enough, we'll see the splitting field of F. And I switched. Oh yeah. Right. So right. So if I take some other random symmetric polynomial in n variables, then and then I plug in alpha 1 through alpha n, then into G, just any symmetric polynomial, and I plug in the n roots of. Oh, I should prove this, huh? I forgot to mention that. Okay. So sorry. So I'll prove that in a second. So if G is a symmetric polynomial in n variables, then G with alpha 1 through alpha n plugged into it is an element of F, the base field, not of the extension, i.e. So the thing you want to imagine is that, well, or e.g., if F equals Q, then plugging the roots of f of x, which in principle are could be some horrendous looking expression involving square roots or cube roots or fifth roots or whatever, or actually in practice it might not have any, as we'll see eventually by the end of the course. Those numbers alpha might not have any sort of convenient expression at all in terms of the rationals. Anyway, but still, if your base field is Q, then plugging the roots of f of x into the symmetric polynomial G gives you a rational number. So that's kind of a strange thing, actually. I mean, if you sort of understand it, it's a pretty weird result that you can imagine sort of plug. Well, I guess I'll do an example. Yeah, let me do an example. So let's see. So for example, yeah, I'm just sort of undecided whether I should type or handwrite, but let's try typing first. So example, suppose f of x. I am now totally winging this. This is a terrible idea. So So the alphas are now I will handwriting. Now I will handwrite. So let me go back to the pen. So alpha 1 equals root 3, and alpha 2 equals minus root 3. So those are the two roots of those are the two roots of f, and there's and we have some. I guess we didn't really need a splitting field to state this, huh? Oh well. Anyway, so we saw that g of u1, u2, u1 comma u2 is u1 squared u2 minus a plus u2 squared u1. And the claim, well, this is not going to be very interesting. The claim is that if I plug in root 3 and minus root 3, I'm going to get a rational number. Well, I guess that's going to work out here because this is going to be u1 squared, which is alpha squared, which is 3 times minus root 3 plus minus root 3 squared times root 3. And look, this is in fact rational. It's not a very interesting rational number, but it is rational. And that sort of wasn't, at least it wasn't obvious to me like about 2 minutes ago that this is actually going to work out. It's one thing to sort of believe that the theorem is true, and it's always another thing to actually get on the airplane that's been designed using your theorem. That's always like another level of belief. Or take the vaccine that's based on your theorem. I don't know if I'd ever want to do that. Anyway, yeah, but there we go. This does happen. It does happen when you plug in. Here's a symmetric polynomial, and you plug in root 3 minus root 3. Oh, look, it worked. I got a rational number, even though the number is 0, so it's not quite so exciting. It might be more exciting if you had something like 1 plus root 3 over 2. You might try something more interesting. I don't know, 1 plus or minus the square root of 3 over 2, etc. So no matter what crazy thing you plug in over here for the two roots of the symmetric functions theorem, this corollary to the symmetric functions theorem says that no matter what kind of pair of solutions to a quadratic you plug in to this polynomial, you're always going to get a rational number. Wow, nuts. Anyway, yeah, what do you actually get here? Yeah, I mean, actually, that's a good one. Yeah, so try that one. I can see that'll work, and I'll say if you especially if you don't believe it, try that yourself. That's really fun. And here, it's probably better to write this as this is as the so this is actually maybe more like omega and omega squared, where omega cubed is the cube root of unity. Oops, minus 1. Sorry. Minus 1 plus or minus square root of 3 over 2. Anyway, yeah. So that's the way to check that. That's fun. Anyway, oh yeah. Geez, I didn't leave quite enough space to prove the proof of the corollary. I guess actually there I think I want to type, but it's actually the corollary is not too hard to prove. It's actually very short. This is the lovely thing about this. So proof of corollary. Since G is symmetric, a symmetric polynomial, it is a polynomial function of the elementary, I guess I should say, by the symmetric functions theorem. So G is a polynomial function of the elementary symmetric functions. Yeah. It's a polynomial function of elementary symmetric functions. Great. But if you plug, I guess I'll switch to 10 for a minute. If you plug alpha 1 through alpha n, so if you plug in those roots of f into into an elementary symmetric function, you get, oops, I should leave more space here. You get one of the coefficients. Coefficients. Oh my God, I cannot spell today. How many times it going to take me to type the word coefficients? You get one of the coefficients of the polynomial f of x, which is a polynomial, i.e. an element of f. That's the proof. Isn't that lovely? So that's actually pretty cool. You know, I think I definitely on Sunday night I did not understand that this is a pretty cool theorem, and now I actually do that. Applying this to an example, this is pretty cool. Yeah. So right, but the point is, again, so the theorem says that if I take any symmetric polynomial and I plug in the roots of f, then I'm going to get a. You want to think this is a rational number, and the reason that works is because if I whatever this expression is, g of alpha 1 through alpha n, it's a polynomial combination of elementary symmetric functions, and we know because that's essentially the definition of the elementary symmetric functions, that if you plug in the roots into the elementary symmetric functions, you get the coefficients of that polynomial, right? Because the whole point of the elementary symmetric functions is that they express the coefficients of a polynomial as a function of its roots. Whew. Okay then. Any questions about that proof? I can't quite. Well, you know, I can try to. Let's see what happens. I make this even smaller. No, that was too small. Let's try this. No. Here, this. No, this doesn't fit. Never mind. Okay, so yeah, so sorry to switch back and forth between this, but you know the idea. Yeah, actually, this shows the application that if you take any symmetric polynomial and you plug in the sort of all the roots to a polynomial, some other polynomial, then you get a rational number, and the reason is because this thing over here is really just a polynomial combination of elementary symmetric functions. No, that's actually pretty cool. I mean, it's kind of a digression from Galois theory, but it's again still pretty cool. All right. So, any questions so far, or are we good to move on from symmetric functions? Okay. I guess there are no significant objections. So let's go to the discriminant. Okay, so now, now I want to think about. So now what I want to do here is I want to think about this polynomial, which is the product, and now I want to look. Oops, I forgot a variable here. So I want to insert here. So let's consider the ring. The ring of polynomials in the variables u1 through un and the variable x. I forgot about x. And so if, again, if I take this product, I just think of it as like a polynomial and a bunch of unspecified variables, then I get some expression. And then, as you know, as we were discussing last time, you get some expression here in terms where each of these S1s, so each of these S sub i's, the S sub i's, that didn't come out so well over there. Each of these S sub i's are an integer polynomial in u1 through un. Okay, so now we have this again. We have that setup. So the discriminant. So there's a sort of general setup. This is just some sort of strange combination. I guess this is really we're suddenly have turned into an algebraic combinatorics course. Actually, I don't myself know a lot about symmetric polynomials, but this is actually a great topic of study. Hey, that is actually a very good. What happened? Oh, there's my tools. This is a very good. So here we go. Master's thesis project, or it's a little more. So this, I mean, it's not a research project, but it's a very good expository project. Let me say expository. I don't know much about this in detail, but I know there is a sort of interesting theory about this. Symmetric polynomials and generalizations. And there are a lot of generalizations. So there's a whole sort of, there's a whole theory. You can really take this pretty far. I at least have seen talks about this where people talk about generalization, very broad-reaching generalizations of symmetric polynomials. Anyway, sorry, that's a bit of a digression there. But if you're looking for a master's thesis project where you sort of learn the kind of the book report type, the book reports are good. You learn a lot. You learn a significant chunk of math and write and sort of explain it. Anyway, sorry, but if you're looking the bit of a digression, but if you're interested in that, in any case, the discriminant in these terms, the discriminant of this polynomial is defined to be d of u. So right. So this is a little bit. This is a piece of notation from that's used in Artin. I think this maybe not quite explained. So when you see something like, so when you have a bunch of u sub i's floating around, and you see something just a u with no subscripts, often this will mean this is an abbreviation for u1 through un. So this is. So as to avoid writing u1 through un over and over and over again, this is really just saying this is a polynomial in u1 through un is defined to be the product of all pairs I comma j, all distinct pairs I comma j of ui minus uj squared. So it looks like u1 minus u2 squared, u minus u3 squared, and so on. Okay, so that's the discriminant. So this is a symmetric polynomial, and so by the symmetric functions theorem, it follows that d can be written as an integer polynomial in S1 through Sn. Great. And so if alpha 1 through alpha n are in the field, some field k. Oh right, yeah. So that's fact number one. And why is that true? And this is just because d is a symmetric polynomial. Should we discuss why d is a symmetric polynomial? Why it's invariant under permutations? Or maybe I guess it's because let me just say it's because this is really a function. This is really summing, sort of taking a product over all pairs, and the pairs of the two element subsets of a set n are invariant if you write the subsets in a different order, and therefore d is a symmetric polynomial. All right. Right. And so and the other thing to note is that by definition, if alpha 1 through alpha n are just alpha 1 through alpha n are just sort of random elements in some field, or then or even just in random elements of some integral domain, I guess, then d of those elements, again, this is abbreviation for alpha 1 through alpha n, is equal to 0 exactly when two of those elements are equal. So I think we'll at some point we'll use this later, but the idea of this is that D detects repeated roots. Here's yet another. Oh yeah, right. Well, this is something that those of you who are teaching college algebra know very well. So this discriminant is the same, as we'll see in a minute, is the same discriminant that you've been teaching in college algebra, and in fact, you know very well that having a zero discriminant means that you have a repeated root. And so yeah, so even in this general definition, D is something that you can use to detect the presence of repeated roots or not. I guess that means, I guess that means that D has some subtle connection to the derivative. Interesting. There must be something. You must be able to get some mileage out of that. All right. So I'm full of digressions today. Anyway, so that's repeated roots. So let's look at oh right. So this is, oh right, this is a piece of notation that I prepared this last time. Let me sort of explain what this notation is. So D is discriminant in the U sub I. So if I think sort of as defined. So if I think of the discriminant as a function of the U sub i's, and then you know that's a polynomial D. But delta now delta for delta, remember this observation here shows that D can be written as an integer polynomial in the S's, and we call that integer polynomial delta. So so delta is the discriminant written in the S sub I. So in other words, while the discriminant is defined to be is given a definition in terms of the roots of a polynomial, delta is the discriminant written as a function of the coefficients, which the symmetric functions theorem tells us must be possible. Right, the symmetric function theorem says that that D is a polynomial combination of the elementary symmetric functions, and so which means that there must be some way to write any sort of arbitrary discriminant as a function of its of the coefficients of your original polynomial. Okay, and so now here, all right, now so here we're gonna sort of rewrite. Well, here's the degree 2, and here's the degree 2 version, and we're about to obtain a very familiar formula. Let's see. So again, right. So remember we had this equation that keeps popping up over and over. The product of x minus ui is equal to some written out as with its coefficients in terms of elementary symmetric functions. And so this is remember this is the definition of S1 and S2. Or you can think, or if you're teaching college algebra, you can think about this is sort of like the definition. You know, this is like x squared minus bx plus c. Right. This is this is sort of telling you how b and c relate to U1 and U2. And so now, if we define, we have just defined the discriminant of this sort of generic degree 2 polynomial as quantity U1 minus U2 squared. that's going to be equal to u1 squared minus 2u1. See, look, I'm passing college algebra right now. Minus 2u1 u2. They're not handwriting, sorry. Plus u2 squared. And so, right, and so remember, and the elementary symmetric functions are that S1 equals U1 plus U2, and S2 is equal to U1 times U2. And after some thought, you can sort of, well, just after some guesswork, this is kind of like, it's pretty close to, oops, this expression that we have here is pretty close to U1, oops, U1 plus U2 quantity squared. It's like that, except when you do that, that gives you plus 2, 1 U2 instead of minus 2, 1 U2, minus 2 U1 U2. That's very hard. That's hard to say. But so I guess to fix that, to go from plus 2 this to minus 2, from plus 2 this to minus 2 this, we have to subtract off 4 U1 U2. All right, and so this is correct and that's correct. And so now, so this is equal to S1 squared minus 4S2, aka what? B squared minus 4C. What? What? I'm gonna go a little Keanu here. Yes, it's the formula that you know and love, but and perhaps have even taught recently. And you know, and it really is B squared minus 4AC because A is equal to 1. Right. So yeah. So the discriminant, as given the sort of very natural general definition, is in fact the thing that you know. It's B squared minus 4AC or B squared minus 4C. What? I thought that was pretty cool when I just sort of realized it preparing for this section. Any questions? So does that make sense? Say yes or ask questions. Okay. There are at least no objections, unless somebody's sort of sitting here. Actually, let me pull back out to the whole page view. Yeah. So just in case somebody's just wants to soak this all in before asking a question. So yeah, those of you, I think it's actually now the majority of you are teaching college algebra, and so you can truthfully tell your students that, hey, I just did the discriminant myself today. Whoa. Okay, yeah, let's move on. So whoa. All right, so now let's do degree 3. Now, the truth is that delta is really sort of, you only want to do this for degree 2. If you write this out, if you look in Artin, there is he actually has written out the whole formula for the discriminants in terms of S1 and S2 and S3, and it's like super complicated. However, it is true that after a change of variables, you can get this down. It's just sort of like completing the square. You can assume your polynomial has the form x cubed plus px plus q, in which case, after some much more complicated version of what we just did up here, you get oops. Here we don't really want d of u. What we actually want here is delta of p comma q. So after so I think that sort of shows the distinction. I guess let me actually write that out. So d, remember, d of u1, u2, u3 is by definition oops. u1 minus u2 quantity squared times u1 minus u3 quantity squared times u2 minus u3 quantity squared. So that's what d of u looks like, and it turns out that in the case where the square term is equal to 0, a whole bunch of stuff cancels out, and you get the delta of p cubed equals minus 4p cubed minus 27q cubed. And so this is something. And let me actually, I have my, hang on a second. Let me check. I got this formula right. I think I feel like I can reliably get that plus or minus. But I want to make sure that I actually got the signs, SIGNs correct. Discriminant. Yeah, there we go. So good. So that's what the discriminant looks like in terms of P and Q within the convention. In the slightly different convention, where Q is given a plus sign instead of the minus sign that we have. So this would usually have a minus sign over here, but if you give it a plus sign instead, then you get minus 4p cubed. Well, I guess it doesn't really matter. Sorry, it doesn't really matter because the cube is, you put the minus sign on, it's just going to square it anyway. So yeah, the point is that delta is minus 4p cubed minus 27q squared. And it turns out, anyway, so it turns, as we shall see, so we'll see later that just as the discriminant determines how complicated the quadratic formula appears for degree 2. The discriminant determines how complicated the cubic and quartic formulas appear in degrees 3 and 4. So there. So one of the things I think we will at least mention, even if we're not, I'm not sure. I can't remember if this book actually looks at the quartic formula. I think definitely the cubic formula, but I'm not sure if there's the explicit quartic formulas written out. But so just to, so what do I mean? How complicated? Well, so you remember that if actually, let me go back and retroactively add something in here. So we observe that if the discriminant is equal to 0, then the quadratic formula becomes essentially x equals minus b over 2 because a is and that's just because a is equal to 1 in our I guess I should, there's no reason to start over 2a. So we saw in the quadratic case, if that your discriminant is equal to 0, then the quadratic formula becomes a rational formula. And what we see over here is that what we'll see later on in the cubic case, and I think also at least there's some discussion of it in the quartic case, even if there's not an explicit formula. The explicit formula is kind of hairy, if I remember correctly. Then the value of the discriminant tells you exactly how complicated your cubic and the cubic and quartic formulas appear to be. Whew. All right. So anyway, so are there any questions about? Yeah, I guess I kind of omitted I completely omitted the derivation of how to get from d to delta for the cubic, but does that kind of make sense as to what at least the definition of d and delta are? So are we good? Or are there any questions about the definition of what d and delta are in the cubic case or in general? So should we move on? All right. I think everybody's surrendered at least. Okay, so let's talk about splitting fields. Right. Yeah. So I guess I think 952. We'll definitely sort of talk about splitting fields, and then we'll talk about a little bit about at least a little bit about F automorphisms. So as we've already said a couple times, to say that K extension K of F is a splitting field of little f, a polynomial with coefficients in big F, means that little f factors linearly in K, and K is the smallest possible field in which that happens. Because in order for little f to factor linearly, you definitely need K to include all the roots of f of x. Otherwise, these wouldn't be each of these linear factors would not be a polynomial in coefficients in K. So so some straightforward consequences of this definition include, well, one, every polynomial in F has a splitting field. Proof: you keep adding roots until F factors, and then you just go by induction on the degree of the F. And every finite extension is contained in a splitting field. Yeah. So yeah. So and why is that? It's because proof finite extension is obtained by adjoining finitely many elements. You can think of it as doing it one at a time. So there are only finitely many sort of minimal polynomials to consider. So split all of them, and or rather split their product. Yeah. So there's something a little bit subtle about dealing with the splitting field of a polynomial, which is that sometimes we will require f to be irreducible, and sometimes we won't. And so far now we are not requiring f to be irreducible. I guess I should type that in. F might parens f might not be irreducible. But the definition of splitting field still makes sense. But sometimes we will actually require f to be irreducible in order to get certain results to be true. I mean, otherwise they won't be true. Right? But so far we haven't had we have no requirement for f to be irreducible. So there's our first. So is everybody good with splitting fields and our first consequences so far? Okay. All right. So and so here's the sort of main result of that will sort of use. And here I think maybe so the proof is like mildly complicated, and the result is kind of cool, but the proof is sort of mildly complicated. And so I think probably I'm just going to sort of well, no, I'll zoom in. No, I take it back. I will zoom in. I'll do my usual thing. I'll zoom in and then sort of pull back at the end. So the splitting theorem says that if K is a splitting field of little f, then if you have any irreducible polynomial G with coefficients in big F, and that G has at least one root in K, then G must entirely split in K. So that's kind of weird, right? Like usually, oh, actually, I should go back and do a non-example. Actually, that's probably more useful than what I'm about to do. So let's do a non-example. So I apologize for this being a little bit out of order. Well, this is happy out of order. Let me add in another page here. Yeah, so here's a non-example. It's a sort of useful non-example. Take K to be Q adjoin space for this the cube root of 3. I think I better switch to pen here. Cube root of 2. So it's important to realize that it's possible for things to sort of factor and not split. So that if you look at f of x, if the sort of irreducible polynomial corresponding to that, x cubed minus 2, then so that's irreducible in the rationals. Oh, by the Eisenstein criterion. I mean, you knew that was true, but it's by the Eisenstein criterion, and it factors in K as x minus the cube root of 2 times, let's see if I remember to do this correctly, x squared plus the cube root of 2. Oops, what happened there? That was weird. Cube root of 2 x plus cube root of 2 squared. Yeah, that works. I think that's right. Yeah, that's right. So that's one of the more obscure kind of factorizations that you learn in college algebra, but it actually happens to be pretty useful over here. But the thing is, so this factors, and the point is, the point of this is that this factors once but does not split. Factors once but does not split because, well, if for no other reason, does not split because, for example, the other roots of f are complex. So I guess at the very least we can conclude that K is not. So I guess I should. So K is not the splitting field, or it is not a splitting field F. And again, we also as we'll see, we do not have, and the splitting theorem, see below, we're coming up in a minute, does not apply. All right, so the weird thing, if you really don't, if you consider most of the time quadratic extensions, then all kinds of nice things happen that don't happen in general. And when you get to the cubic, well, it turns out you need to sort of add on x. You can't just add on the cube root of 2 to find all the solutions to this equation. There's like this other stuff that you have to that you have to account for. I guess I should also point out that this is a completely real field, and so there's no way to factor this thing because the square term here, because you have to use the other roots are complex. Anyway, Right. So so the point is K is not a splitting field of F, and the splitting theorem does not apply here. So yeah, I guess I wanted to sort of draw a contrast because a lot of the times the first sentence will say, I mean, basically in order to apply Galois theory, the first sentence you say is let blah be a splitting field, and so sort of the most I just want to point out that some of the most natural extensions that you consider, as long as you have a degree greater than 2, are actually not splitting fields. Oh, I guess I should mention that as well. Also true, but not obvious. Oh, yeah. And so, and as we'll see, it also follows that K is not the splitting field of anything. Not a splitting field of anything. Because here's an irreducible polynomial that has one root here, but does not split. Yeah, as we'll see, it follows from the splitting theorem. K is not a splitting field of anything. That's much less. I mean, here we've already sort of proven that K is not the splitting field of F, because, well, we tried to factor F and it didn't work. And it can't possibly work because you can't go any farther without using non-real numbers. It's much less obvious that there isn't some other mysterious polynomial for which K is a splitting field, but we'll see in a minute that K is not a splitting field of anything. So yeah, before we get to the splitting theorem, are there any questions about our non-example here? Okay. Yeah, let's get to the splitting theorem. And here I just want to the idea of the proof is not that bad, and but the details are a little bit involved. So I just want to sort of sketch the idea of the proof. To start again, suppose extension K of F is a splitting field of little f. Then if little g, some other random polynomial with coefficients in big F, is irreducible, and has at least one root in capital K, then g of x must split in K. So it's not just so the point is, so not just F that splits completely in K, it's any polynomial that has any roots at all. Not just F that splits in K, it's any polynomial with roots, any root in K. And so here, if K, so what that means is, going back to our non-example, if you have a field in which any irreducible polynomial fails to split, but factors a little bit but not completely, then you cannot have started with a splitting field. Okay, so again, the point is that if you have a splitting field, if you have a field generated that's defined by having one polynomial split, that's the splitting field of one polynomial, then any other polynomial either stays irreducible or splits completely. Cool. Or sorry, at least it has no linear factors or splits completely. My bad. So here's the idea of the proof. I'm used to saying the word ideal, huh? Here's the idea of the proof. Suppose beta sub 1 is suppose we have a splitting field K of some random polynomial little f, maybe not irreducible, and you have some other polynomial G which is irreducible and it has one root in K. So to say that K is a splitting field of F means that K is generated by the roots of little f, which means because so why is this? I should because beta is in K, because beta sub 1, oops, because beta sub 1 is in K. Oh no, what was that? There we go. I didn't mean to do that. Okay, because beta sub 1, what? Oh, never mind. Because beta sub 1, there we go. Because beta sub 1 is in K, there must be and because K is generated. Oops, K equals capital F. Yeah. Join alpha 1 through alpha n. Then any element of capital K must be a polynomial combination of alpha 1 through alpha n. That sort of follows from our knowledge of finite extensions. So that means that Sn acts on polynomials in n variables. Oh, sorry. So first of all, we know that P1, we have some polynomial P1, some polynomial combination of the alphas is equal to beta 1. All right. So that any questions so far? Whew, especially since after I messed that up a couple times. Okay, so now we have some kind of random polynomial in n variables, not necessarily a symmetric one, but we can actually take that and symmetrize it. So we can kind of like, if I may call back to something we did at the very beginning of class, just like so if you take a sort of, there we go. Hope I didn't make any motion sick just now. But if you take a sort of random polynomial in two variables, you can symmetrize it and get a symmetric polynomial. So if you do the same kind of thing here, if you start off with P1 and look at all of its images under the action of Sn, then you get a bunch of different monomials or polynomials P1 through Pk, and so let's take each of those. So beta 1 was the first root of G that's contained in capital K, and now we have these other elements beta sub I by plugging alpha 1 through alpha n into the other polynomials, and so and now we form the now let's just sort of, well, for reasons best known to us, well, for reasons that we'll see in a minute, let's form little h of x. Let that be the product of all the x minus betas, and so we get this thing here. So because of this first term here, the GCD of G and H is not 1. So G has some common factor with H, and then because if we can show that H has coefficients that are rational, so to speak, that have coefficients in your base fields, capital F, since G has a common factor, then in that case, because G has some common factor with H of X and is irreducible over F, then G has to divide H. So to make a long story short, there's some sort of clever details in here, and I will therefore omit them. Each of these coefficients, b sub 1 and b sub 2 and so on, is a symmetric function. Turns out to be a symmetric function of alpha 1 through alpha n, and it's therefore a polynomial in the coefficients of f. That's the symmetric functions theorem again, which are in f. And this essentially follows. I mean, if you really want to get into the details, they're in Artin, and what's really going on here is that this is a symmetric function. So these b's are a symmetric function of the betas, so to speak, in k variables, and then you're plugging in things that have been symmetrized under the action of Sn, and so the whole result has to be invariant under the action of Sn. Yeah, that's a sketch. I know that's kind of vague, but It's just and just a sketch of what happens. But the idea is that because you have symmetry, because you're building something symmetric at every stage, you have to end up with something symmetric. And which is therefore a polynomial in the coefficients of f, because by the symmetric functions theorem, and so you get something rational. All right, well, okay, so that was just that I think that deserves maybe not a smiley face, but a sheepish grin. I think I'm willing to give up there. So are there any questions? I think that the main thing. Actually, let me pull back to sort of look at the idea of the proof. But I think really the main thing to understand is what the result says. The result says that if you have a splitting field, then any other irreducible polynomial in the base field with coefficients in the base field either has to, if it either remains irreducible or has no roots or splits completely. You either have one, either have all your roots or none of them. Which means, for example, that because this field here, Q adjoined Q root of 2, has some irreducible where you have one root but not all three, then this K must not be a splitting field. So this is somehow, I guess maybe the sort of lesson for later is that nons will soon think of non-splitting fields as abnormal. That's actually a pun. Remember normal subgroups? It's actually in some way. Unintended. Because as we'll see in a bit, non-splitting fields as being, well, abnormal is a bit harsh, not normal. Because as we'll see later on, the non-splitting fields correspond to not normal subgroups. Anyway, and I think it's almost 10:15, so I think that's the right place to finish the adjourn for the day. Any questions or any questions before we and so next time we'll get into 16.4 isomorphisms of field extensions. Good. Okay. Is everybody good? Okay, so yeah, as my PhD advisor used to say at the end of every lecture, let's give up for the day. So yeah, we'll start next time with isomorphisms. We'll start on Monday with isomorphisms and field extensions. We have a problem session on Friday. I hope at the usual time of 10:30. I hope you can make it by Zoom and work on some stuff together. Work on problem set 8 together. And let's see. And so I get so again, I know so technically we had some deadline, a written deadline of today for exam 2, but if you need a couple more days or longer, just let me know, and don't sweat it. And I'll try to get, and especially I'll try to get problem set 7 graded as soon as I can and sort of catch up on everybody's homework. So if you want to go and change your exam after seeing how the results from problem set for the grading of problem set 7, you can go ahead and do that too and sort of resubmit. Anyway, take care, and I'll see you on Friday or Monday. Bye.